Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
We are. There we go.
Yes. Hello, and welcome to another episode of Ask Us Anything About Electrochemistry. I'm Alex Baroff. This is my colleague, Dr. Neil Spinner, and welcome to the live stream. This is an opportunity for you to ask us. I'm just going through the boilerplate stuff, but it's just an opportunity for you to ask us any questions about electrochemistry. You may have attended some of our webinars, YouTube videos, just phone calls, just whatever interaction, and we get a lot of questions, and this is the time to really take a deep dive into your questions about electrochemistry. The questions that are best for this kind of platform for live streaming are questions that are not ultra specific, but also not too super broad. So the really broad ones, you really need to have, say, like a full webinar that's like several hours long. And the specific ones are just too specific for us to really know about, say, your specific electrochemical system. So just keep that in mind. Maybe there's clarification about a specific technique or even a general electrochemical system that we might be able to provide some kind of information on. We usually do this for about 2 hours. And if you can't make it to the live stream and you're watching this after the live stream, which I know a lot of you do, there should be, you won't necessarily get the timestamps until a few days later, but the questions that are all asked during the live stream will be timestamps in the description below. And that can be found probably a few days after the live stream ends. Lastly, also, we were talking about and having some review over how the live stream is doing, and we really appreciate your support and coming to visit us. This is like episode 41, so I've been doing this for quite a while. If you ask a question, type it into the chat. You don't need to repeat multiple times spamming a question. If you do spam anything, you will get kicked out. We will block you from the live stream. We want serious, important electrochemistry questions. We don't want to take other people's time who have genuine questions about it. So if, of course, you've asked the question and we've gone through a bunch of things and we may have forgotten about yours because there's a lot of questions sometimes, you can send us a reminder, and usually that's very good and that's appropriate. We apologize ahead of time if we mispronounce anybody's name because it's just a YouTube name. So when we're addressing you, And I think that is about it. If you're a tier 1 or a tier 2 YouTube member, you have an opportunity to join us on Restream. Right now, this is being live streamed to X, or Twitter, and YouTube. So you can join us on Restream, which is the broadcasting platform to actually share any data. And if you want us to actually look at a voltammogram or some EIS data that you want some help with.
And you can talk to us instead of typing your question, which
Correct.
will perhaps be easier if you have to describe the question or the situation.
Yeah. So I think those are all the basic boilerplate things. It looks like we do have a question, I think from Tarek. And let's see. So Tarek is asking, welcome back. Hi all, is there a plan for Pine to have their well-known RDE operate based on air pressure instead of using an electromotor? And this change could help avoid introducing electrical noise, which is undesirable when performing sensitive techniques like EIS. Oh yeah, and he's just making a comment about spam.
Yeah.
We have reached a few points where there's
It's happened
spam.
a few times. Actually, just as a note, it's tricky sometimes to determine whether someone's really anxious to get their question answered or they're trolling.
Yeah.
This is the internet, and we know how the internet works. We're not born yesterday.
Yeah.
So anyway, just for what it's worth, we do appreciate, like, for example, the classic example is, as Alex said, don't ask questions that are too broad or too specific. And then sometimes what I'll say is, don't say something like, what is electrochemistry? And we have gotten people who have actually asked, what is electrochemistry? And my first thought is like, okay, you get what you asked for. This is the internet. But some people have been like, no, I actually really am curious. Like, they must stumble upon this live stream and they genuinely don't know what electrochemistry is. And so it's hard to judge.
Yeah.
For us, we do our best. We are certainly happy to answer questions as complicated as we're able, and as less complicated for what it's worth, right? We're not trying to judge questions or anything like that. We've always tried to keep this as a inviting kind of a forum. So for what it's worth, to your question though, Tarek, right? And we have one other kind of topic that was from someone last week. I think there's a really interesting follow-up on IR compensation. I think Alex mainly will get into in a moment. In short, to your answer, the answer is no. And partly the reason is, I would say, probably twofold. The first is that that's just a tremendous R&D project that is simply not going to happen. I'll just be honest with you. It would be certainly not trivial to fabricate a rotator driven by air pressure as opposed to an electric motor. All I will say in that regard, as far as rotator R&D and manufacturing is concerned, is that it looks really simple. It seems like it should be really simple. It's a motor and a stick and it spins, and it is tremendously more complicated. There are a lot of things involved. I can just say that pretty authoritatively, as we work for the company that basically invented the electrode rotator, and it's been doing it the best in the world for about 50 or so years. And it's not trivial. It seems like it should be easy. So the first thing is that the R&D of that would be really tremendous. Now, the second part of your question is a good one, which is to say electrical noise can be introduced from an electrical motor. That is true, though the impact of that, in particular in our newer rotators, is less, in my estimation, less of an issue because we select smart choices. For example, the metal housing around the motor, we test for its what is it? ESP? What's the ES?
Like EMF or electromagnetic fields or noise.
Electros. It's like ESP. I'm terrible at this. We test for the
electric noise.
Electrical noise, exactly. Yeah. Out of it, both vibrational noise, electrical noise, like audible noise. Like we do a lot of testing in that regard, and so we actually do what we can to make that. Of course, doesn't mean that there's no noise or no impact. For example, if you're doing a sensitive technique like impedance, but for the most part, we mitigate that by, you choose a metal housing effectively that's like a Faraday cage, right? And so that does mitigate that to a good degree, I would say. but that is a good question because the rotation in the motor can certainly be, problematic if you have really sensitive techniques. It's not an irrational thought, I would say.
Yeah. It's very interesting. I'm actually just thinking of like an air pressured rotator. Like, does that mean you would have like fins or something?
I mean, it'd be like a hydraulic. It's almost like a
that blows?
hydraulic something. It's like you need. I mean, that would open other questions too. It's like you'd have to have like a compressed air source of some kind, and that would vibrate itself and possibly whatever. It's like, does that make like literally? I'm thinking you have the rotator here, right? And there's no electrical motor, but you have like an air compressor over here, and that's like buzzing and stuff. So it's shaking the whole lab bench. I know
that's also true.
Like logistical stuff, but it's like maybe your lab has a pressurized air source or something. But yeah.
All right. Well, we do have a couple questions. I'll move on. I'll talk about the IR compensation thing later if there's no questions. But as people come in and they have questions, we can talk about this. So let's say George has a question. Hello from Brazil. Very good. Inquiry. In linear voltammetry tests on duplex steel pieces using KOH as the electrolytic solution, I obtain a linear relation for the peak potential and the square root, he's got a continuation, and the square root scan rate. The EP values decrease in samples with higher sigma phase concentration, higher amount of chromium and molybdenum, when I expected an increase in EP as the sigma level increased. What could this, what could this phenomenon be? And then I think there's a further comment, considering the film formation process on the material surface. Think about this.
I have to like look at this and reread it. It's quite a lot.
This is a lot.
This may fall under the category of a question that's a little too specific for us to be easily able to answer. It is quite comprehensive here. So there's a duplex steel. Okay. You do voltammetry. So it looks like you got a linear relationship for peak potential and the square root of the scan rate. So I guess that means that you've used the Randall-Sevcik equation and you're obtaining the kind of correlation that you would expect given that equation. So I guess I'll just, for those who, let me
and also just a point of clarification. When you say EP, like we're talking about the peak potential as the peak potential current, or is it is the peak potential the thing that's moving, is moving, or is the current at the peak potential the thing that's increasing?
I'm thinking it's the voltage just moving, simply because he made the point that the peak. Oh, I'm sorry. Maybe you're right.
Well, that's a point of clarification.
Yeah,
we just want to clarify.
And that is actually a good point to clarify, because I actually realized that, I'm making the assumption the Randall-Sevcik equation is what you mean, but actually you put that the peak potential and the square root of the scan rate. That's not the Randall-Sevcik equation. The Randall-Sevcik equation describes the peak current and basically the square root of the scan rate, right? That's the relationship here, is that effectively you can see it on my screen, that the peak current of a voltammogram is proportionate to a lot of constants and the square root of the scan rate.
Yeah, so we just want to clarify, because maybe you meant that, but I don't know for sure.
Yeah. So the E value decreases. Yeah, I think that probably the short answer to this is that we just don't know. This is rather specific and complicated. And frankly, I would have to know more or look up, like, for example, at a quick glance here, you're showing that the potential value, for example, at the peak is changing as the concentration of certain elements changes. That tracks from the perspective that like every element has its own standard potential. And so I guess, again, I'm not going to like spend a ton of time, because I don't like chromium and molybdenum, obviously certain redox.
Okay. All right. Here's saying
corresponding to yes, I think
IP.
so. He does mean the Randall-Sevcik. Yeah. So basically,
so it is Randall-Sevcik.
I think what you're saying effectively is that the shift in your like peak potential. Basically what effectively seems to be the thermodynamic equilibrium potential is moving in the opposite direction you would expect. And I'm guessing that you're feeling that way because you are assuming, for example, that the standard reduction potentials for chromium and molybdenum, for example, are so it's, you expected the increase. So I'm guessing chromium and molybdenum have like redox potentials that are like, you're thinking they're more positive. And so if you have more CR and MO, the, equilibrium should be up here, but it's actually moving here. And the only thing I could kind of say to that from experience and just from like sort of like thermodynamics is that the equilibrium potential, especially in something like steel that consists of, basically mostly iron and then, carbon, chromium, molybdenum, and maybe a little nickel, like a lot of elements. It's a pretty
alloy.
Complicated mix of, a lot of different redox species. And so you're going to get some, I don't know that it's as simple as exactly saying like, if I add more CR, right. And my standard potential was like 200 and CR's potential is like 400. So if I just add more CR, it should get closer. Like maybe that will happen, but you might have other odd interactions in your steel composition that can, like film formations and things like that, that can impact where that like thermodynamic equilibrium potential will be. So I don't know how easy it is to draw direct conclusions about where you think it should be just based on a little bit of a higher, percentage of a certain element, for example.
Yeah. I think if you also tell us a little bit more about, I know you've given us a lot of information. This may honestly be a thing where like you need to be like a tier 1 member to actually show us like, what does this voltammogram look like? What's a little bit more of your system? Like, are we looking at the reduction of chromium and molybdenum onto the steel, and you're talking about film formation? Are you referring to a deposition that's occurring? Like, is this a potential deposition type of thing where you're forming different layers based on the potential, this is like under potential, over potential deposition, and you actually may have some shifting redox peak. So there's a lot of questions, I think, at this point. There could be a lot of things happening, but we don't really know for sure. Hopefully that was helpful.
Yeah. Thank you for the question. It is certainly a complex system. So if you're able to give more information, join us live, or we can try to elaborate or look into it a little more. That might be the best answer we can give at this point, right?
Yeah. All right. So it looks like we have a question. Bilal, is it correct to perform Mott-Schottky measurements for high surface area materials, non-planar surfaces? I got a comment one time that it might not be accurate, but I didn't know the reason.
So that's a good question.
Yeah.
I think it is feasible that a comment like that would arise because they would have concerns about should I say, something like the quality of the state of the capacitive layer, the capacitance, basically, if you have a really heterogeneous surface. Something like that, because Mott-Schottky is a technique that is typically done on things like semiconductors that where, and again, correct me if I'm wrong, Alex, like the distinguishing kind of thing here is you have what's called a space charge capacitance effectively. And for something that's like a conductor, you don't have this phenomenon basically. So a semiconductor, because something about the Fermi gap and its lower conductivity, it's a semiconductor. And so basically the capacitance, a capacitor, like ideally and in theory is like a flat plate, right? And then you have two flat plates some distance from each other, right? There's a dielectric in between, and then you have stored charge that way. And so it isn't to say you don't have capacitance if you have some rough looking electrode surface, but I guess maybe that comment, or if there's some truth to that, that if you have some crazy heterogeneity in your surface area, maybe the capacitive effects are not well, I don't know, determined or set up enough such that the Mott-Schottky analysis might not be quite ideal. But to be honest, my impression and my hunch would be to disagree with that suggestion. I don't have a ton, admittedly, I have a lot of impedance experience, but not specifically Mott-Schottky exactly, like in a research laboratory. So, but my hunch as an electrochemist who knows impedance is that you can do EIS on, large surface area materials and nanoparticles and things of that nature. So you can extract charge transfer resistances and capacitances and things like that. So it seems to me like there shouldn't necessarily be an intrinsic reason why a non-planar surface or a really high surface area material, as long as it is a semiconducting material that exhibits a space charge capacitance, for which the Mott-Schottky experiment and measurements are basically built on. As long as it does that, if it has high surface area, then okay. I don't think that would preclude you from doing it.
Yeah,
Excuse me.
I'm trying to read as much as I can in Bard and Faulkner's book. So also Bard just passed away, so it's kind of a sad week in electrochemistry.
Yeah, R.I.P. to Al Bard.
Yeah,
a legend in electrochemistry, and by all, I didn't know him personally, I'd never met him, but by all accounts, a really wonderful man. Obviously, was at University of Texas for a very long time, and our condolences to his whole family, to anybody in the community who worked with him or knew him. We owe, as electrochemists, we owe a great deal of gratitude and debt to Al Bard.
Oh yeah,
certainly, right? He's tremendously brilliant, influential. So just for what it's worth, rest in peace, Alan Bard.
No, absolutely.
But sorry, to the point, just to kind of further that, for example, I'll just share with you our software, and most software programs that have thanks, have Mott-Schottky are similar to this. So I know it's perhaps a little small to see, but this is a Mott-Schottky setup. And so you have basically open circuit, you have the potential steps, and you have your frequency stuff for the impedance. But here, these three, right, the calculation of your flat band potential and electron donor density are predicated on three essential constants: the dielectric constant of the material you're studying, as well as the surface area and temperature. So my point of this is, again, to say, if you have a high surface area, then you just have a higher number you would plug in here, for example, for the calculation. But it's I don't know why that would mean that it doesn't work, right? You just take it into account in the calculation. So I guess that's kind of my feeling on this.
Yeah, in my very brief reading right now, there's nothing inherent about the area of the electrode or of the semiconductor that seems to cause any issues. You have to be careful. I think one of the most important things is really that the doping is very uniform, that the state of charge carriers is uniform across the entire electrode. That seems to be one thing in my extremely brief reading of this.
So
that seems to be very important in doing calculations.
Heterogeneity if the heterogeneity of surface is also including a heterogeneity of the dopant or
of charge,
right? Then I guess that would probably impact it. That makes sense to me, right? So the amendment to what I said is something like heterogeneity of the surface, but homogeneity of the material, so to speak, should in theory lead to measurable, consistent capacitive effects. And so Mott-Schottky should be fine.
Yeah.
in that instance.
Yeah, you could also, I mean, if you want to do a test, like do an experiment with your high area electrode, and then do it again, but like coat it so that only a small area of it is exposed to solution. You could, if you're okay with quote sacrificing one, whoa,
Bless you.
sorry, you could use something like maybe I've used things like Torsil epoxy. That's very electrochemically inert. It just blocks off the other areas of the electrode, and then see if you get similar results.
Yeah.
Hopefully, that might be helpful. Okay. So it looks like Tarek has a couple questions. When was the most recent model released of your RDE? I guess when it comes to electrodes, we introduced a new one maybe a few years ago, the E8 series. And then the wave vortex rotator came out back in 2017. That was the latest one. And the most common popular version of the rotator that's out is the MSR, or the AF MSR CE rotator, as it might be cited in the literature. But yeah, those are all. I mean, luckily, it's not like software in the sense that it's constantly being updated and changed and stuff. It's like it's mechanical. It's a lot of mechanical pieces. Very sensitive, and there's a lot of problems that can go wrong with them. But once it's good, it's pretty good. You don't necessarily have to make a new one.
Yeah, I was just looking for what it's worth.
Mhm.
I was off. I actually thought the wave vortex was 17. You're correct.
It was
I thought
17?
it was. I
Okay.
thought it was 18. I was off by a year. And the MSR looks like was 2007. The current version. There was a version before that, probably the MSRX.
Yeah,
was
maybe
up until
MSR.
then, and then in 2007, it looks like was the year we launched the developed current version of the MSR. That it's had a few changes here and there. A lot of aesthetic, a little bit. Like the paint colors change, little things like that.
Oh yes.
Not terribly impactful as far as performance and whatnot. But the most popular rotator in the world was developed by us, because
Yes.
it's a slight humble brag, but it's for my company, not for me.
Yeah. So Tarek actually has a question. Yes, this is I'm remembering now. A few live streams back, Tarek had asked about determining the time constant for an RQ semicircle. So it's when you when you multiply farads and ohms, you get seconds for the time constant. But what if you have a CPE when you're calculating when you're doing EIS? How do the units actually calculate and transfer out? Because you're no longer working with just pure farads. I think you have this other unit that's and it's like alpha to the
seconds to the alpha over ohms.
Seconds to the alpha over ohms.
Or it's the inverse of that. It depends on how you define your CPE.
Okay.
It's a mess.
It's a mess. Okay.
Yes, very much
so Tarek wanted to ask you about this, because I know you're like the EIS expert.
I've actually covered this. I think I covered this in a live stream some time ago. I would move on to a question. I'm going to try to find it. I have a paper.
Sure.
There's a couple of ways to do it. And I have to kind of track it down. I don't actually remember the
exact thing. That's okay.
I will try to find it though, but it can be done.
Yeah. So I'll take a look at Assad has a question. It may be a more detailed question, but let's we'll read through it and we'll see if we can answer it. Hi, I'm working on MXene materials. I don't know if that stands for something for electrodes. MXenes?
Yeah, I've heard it pronounced MXene.
MXene.
Like Maxine or MXene. I've seen that before. I don't really know what they are exactly, to be honest, but I've seen that term.
So usually it is known that 2D materials are good to be used as electrodes due to high surface area. But area will be effective only if the flakes are oriented vertical or normal to the plane. Okay. But when we synthesize the electrode from any 2D material, In my opinion, it will most probably settle in the horizontal position instead of the normal orientation. Yes. Okay. Makes sense. All right. I could not find anything in papers about flakes orientation. Looks like people do not consider flake orientation to be important. What is your opinion on sheet orientation or flake orientation? Well, this is, I would say, oh, let's see. MXene is a 2D material quite similar to graphene. Okay. So this is I'll just tell you, I think both of us don't really know a whole lot about orientations, but I mean, I think we understand your comment. I'll just kind of draw it very simply so that everyone at least is on the same page, and that at the end of the day, you're really just kind of asking for our opinion. So if you have an electrode and it's like, this is the surface normal, or the electrode's this kind of, black glassy carbon disc or something like that, you may have some material. Being able to draw three-dimensionally might, but if you have a material, it might orient itself as kind of like a square that lies flat on the surface, but you want it to be. Can I actually? This. Let's see. I don't think I can. I don't know if there is a 3D.
Oh, is
yeah,
it like,
three.
do you have to make a?
I can't make a 3D.
If you make like a rectangle and you do like the format, you know what I mean? You can do like 3D effects or something. But I don't know if that's the same as drawing a 3D one.
Yeah. Either way, I'll just kind of draw
Getting
like
all fancy on us.
Yeah, I know. I'm just gonna say like, oh, this thing is now here. So there are these two orientations, and this one is definitely like the orientation that's probably more stable, thermodynamically, and doesn't just drop or fall. But this one is the one that gives you more high surface area. If you have like a bunch of these guys all on the electrode surface, much higher surface area than just this guy here. So the truth is, I don't have any opinion or have any knowledge about how to get these flakes, because it's going to depend on, probably going to depend a bit on the size. How big are these things? How tall are they? And are there things that kind of, link these guys together, keep them in one type of orientation? That helps if you can get something like that to happen. But I mean, you're growing these on the surface. So I don't actually have I don't really have any opinion. I don't have any experience with synthesizing materials and trying to adjust their orientation on the surface per se. The only thing that I'm aware of are things like self-assembled monolayers, which is when you have, some kind these hydrocarbon chains, hydrocarbon chains that are like this, and those are actually kind of poking out from the surface. These do not lie flat like this. That's the only thing. Like, they don't lie flat, they lie like this. But this orientation from a self-assembled monolayer or SAM it only happens, it's a thermodynamic type of thing. Like, thermodynamically, if you give it enough time, it'll actually orient itself this way, because it maximizes van der Waals interactions between these single strands of molecules. But these 2D materials that orient themselves this way, I got nothing. So I'm sorry about that.
Tarek, I have an answer here. I'm gonna go back. Let's see, where is it? Here it is. So yeah, you were asking about the RQ here. So here's just a couple papers. I'll comment on them very briefly, and then I'll put the DOIs in the chat so you can look them up if you want, or I'll show them for a moment here. All right. So this is the first. This is a one publication. Yeah, it's from, I guess at this point, geez, 2016 was 8 years ago. Goodness, where does the time go? So this is right on the extraction of effective capacitance from. So for reference, the answer partly to your question about how to get a time constant from an RQ instead of an RC is through the context, actually mainly of Mott-Schottky, to sort of further that discussion that we just talked about Mott-Schottky. because in Mott-Schottky, you're generally trying to get capacitance, right? And often the fit of data from Mott-Schottky can be done one of a couple of ways, either a series or a parallel combination of resistors and capacitors. And then to get more accurate estimation, sometimes you fit a constant phase element in a different over a range of frequencies. There's a couple of ways. I'm not going to get heavily into it now. All that is to say that you can see this. There's a couple of explanations and equations that are proposed in this paper, and then I have another one I'll show you for sort of having an effective capacitance related to the parameters extracted from a CPE. Now, the thing about it, and I'm not sure if it exactly talks about it in this paper, I'd have to sort of jog my memory, and I've had a lot of discussions with some of my colleagues about this, and it's been some time, so that's why I'm going to only comment very briefly. I have one kind of thing that sticks out that I remember about this discussion, and it's specifically related to Mott-Schottky, but it probably is somewhat general on the extraction of capacitance from a CPE, where you have that odd, Q or whatever variable, right, constant from it. And that is that the either in this paper or in some others that propose solutions to this, there is sometimes it is a function of frequency, which is odd, right? Because it's like if you're trying to determine the capacitance, you're scanning over a range of frequencies or something like that, right? And if you were fitting a perfect capacitor, it's like the capacitance itself is, showing itself over a range of frequencies, but it shouldn't be dependent on frequency. Like it should be dependent on the potential you've set that for that equation, for that experiment. So it was concerning to me in some sense to find ways to convert CPE to capacitance that's dependent on frequency. Because then, well, what frequency do I pick, right? Like if I'm just trying to find that intrinsic property of my material in my electrolyte, it's not frequency dependent. I just want to know what it is. So that's difficult, right? In my opinion. And just to, again, sort of, which you probably can figure out, but it's, as this relates to getting C from Q, you can then multiply it by the R to get your time constant, right? So that's taking this to its conclusion about what you're asking. Here's the first DOI for, I'm typing this into the chat now so you can have it. DOI for getting C from Q. So there you go. There's that one. And then I'll just share another one because there's one other paper that I think it's a little bit of an older publication, not to say that it's bad, but I think it's like 1993. And I think this has some similar kinds of descriptions. Again, I think it's somewhat related to Mott-Schottky coating polymer property. It's a little bit of a difference, but it's a study on impedance, and it it has some discussion of things like this. You can see, I think some of these, again, I'm not going to waste too much time on this, but you can see there's a function of frequency in here that I found problematic and difficult to kind of reconcile if I'm trying to find the intrinsic property itself. But for what it's worth, it's a couple of publications that you can look into. I'm trying to find the DOI for this one. Sometimes the older papers, they don't always put it. If not, I'll just copy it. Maybe it's at the bottom. I'm just going to try to find it. Okay, I'm going to just copy the sort of this part here, corrosion science. This is the, the reference itself. Okay, so let me put that in the chat for you, Tarek. Second reference on EIS, C, and Q, very generally. Okay, so there you go. Feel free to give those a look, and that might help you out. Okay, so did I skip anything? Because I kind of went back here. Let's see.
I think you got it.
Okay. And Assad, it looks like that was what you were just answering. I was looking at papers, so I was sort of absent from what you were answering. I saw you drawing some things, but I was multitasking and trying to
Yeah.
get an answer to Tara's
Yeah, I
questions.
tried to answer Assad's. We also did get a question from Twitter. So
we
Ayla,
did.
we will get to your question soon. There was, I think, another
I see one from X from Twitter.
question
Perfect. Okay.
that did come in, but we will get to it.
We'll get, yeah.
There is a question from Tafara. If I'm doing EIS on, and actually I had to, my restream, I had to refresh it, so I actually lost the question
Oh,
itself.
I have it here.
If you wanted to put it
Yeah,
up.
no problem. So Tafara says, yeah, if I'm doing impedance on a lithium-ion battery electrolyte using a platinum wire, what type of model should I use for fitting? I mean, first of all, the answer to that question is going to depend on what the EIS data looks like. I don't EIS on a lithium. So if you're doing a platinum wire in a lithium-ion battery electrolyte, are you just trying to check is it like a blocking cell, blocking boundary kind of a situation, to study the electrolyte properties? That's sort of my follow-up question. And then, of course, the general answer I can give you is that I would need to see the data. I can't exactly propose. I could propose what typical kinds of, circuit analogs are often found with batteries themselves, but that isn't exactly what you're asking, especially if you're talking about like a platinum wire. It's probably not a battery electrode. You're probably trying to probe the electrolyte itself, which is what it sounds like. So I would need either information about what it looks like, or again, as we mentioned at the top, you can join us on Restream live if you're a tier 1 or tier 2 member on our YouTube channel. There's a community section on our YouTube channel. You can find a link to join us live and show me your data and talk about it, and then I can try to answer. But short of some visualizations, it's a little tricky to propose exactly what model it is. Obviously, I would need to see the data. So, okay. Let's see.
Yeah, there's also a question, kind of a follow-up from Assad about capacitance. Should capacitance in a supercapacitor depend on sheet orientation, whether it's vertical or horizontal? I think my answer, I think in a vacuum, no, the orientation doesn't matter. But of course, because you have different things happening in your electrochemical system, it probably is going to change the capacitance in the way.
I mean, if your surface area changes based on like the orientation of the catalyst, microstructure, nanostructure, whatever, you're probably going to get different capacitances, right?
Yeah. And the only other thing to think about is so like capacitors, sometimes we think about capacitors as like interfaces, and there are interfaces that are in series and there are interfaces that are in parallel. And so the total capacitance, like what you'll end up probably measuring, like if you had just flat orientation, is you would be measuring capacitors in series. It'd be very difficult, if not, I don't know exactly, but like to actually see like, oh, what's the capacitance of each individual capacitor if they're layered up, even if it's in one orientation or the other. But if they're parallel or in series, the capacitance, the equivalent capacitor, will be a different value. So just something to keep in mind. That would be the only thing from an orientation standpoint that I could think of, but that's not to say that there isn't other things could be happening.
Yeah.
Okay.
So looks like the next question from Assad as well is, are you back with like, do you have the questions? That seems
I do have, so I got,
because I have them, but just let me know if you need.
Yeah, I think I'm caught up now because I lost
perfect.
some of the other ones just above it.
Yeah, no problem. Okay, so I have another question. In an EIS Nyquist plot, if I only get one semicircular arc, does it mean that the sample contains only electrochemical double layer capacitance behavior and no pseudo-capacitance? So the first thing that I'm prefacing this with is that I've said this in a few live streams in the past as well. This question of pseudo-capacitance comes up, somewhat frequently. It's a good question, obviously, because pseudo-capacitance, for all of its somewhat in my opinion, what we don't totally know exactly. It's, I find it to be a kind of phenomenon to which it's like something we think looks like or should be capacitance, but it's not really behaving that way. So we just say pseudo-capacitance to like it's something, it's like it's kind of like throwing your hands in the air. Like I'm not exactly sure what's happening here.
I don't know what.
I'm not trying to denigrate it at all. It's just that it's frankly a little bit like hard to tell what's happening. Right. And maybe there's more to it than that. And that's certainly possible. I'm just underselling the phenomenon, which is certainly possible. That being said, despite a possible that I'm not 100%, describing it properly, let's just say, my impression of pseudocapacitance as it relates to impedance data, and what I would sort of assume for myself as a researcher, is that the usage of a constant phase element, which is a non-ideal capacitor, in theory, to me, is a decent application for the phenomenon of pseudocapacitance. So for example, if you have a perfect semicircle, right? Like it's a perfect semicircle and you fit it with a CPE and alpha is 1. That's capacitance, like it's perfect capacitance, right? But that almost never happens. And so if you get a semicircle, it's semicircular, but it's not a perfect semicircle, right? It's like a depressed semicircle or something like that. And you fit with a CPE and you get alpha is 0.75 or something. That is a non-ideal capacitance. And perhaps that sort of implicitly means pseudocapacitance, or at least that could be an explanation of the pseudocapacitive effect. So what I'm saying to you is that if you have one semicircular arc, I don't know that means it's not pseudocapacitive. Like what if you have one semicircular arc and it is like able to be fit with a CPE and the alpha value is less than 1, like substantially less than 1. Maybe that means that it is maybe that's how the pseudocapacitance is manifesting in your impedance data. I'm not 100% sure, but that seems reasonable to me. I typically tend to, and I get this question pretty frequently when I do my impedance webinars. People want to know about what the alpha means, in a CPE. And I tend to describe it as like a heterogeneous, or at least I should say what a lot of people in the literature that I have read describe that as a way to try and explain, well, why is your capacitance not a perfect capacitor? It's something like a heterogeneity of the surface. We just talked about this a little bit, the surface is heterogeneous in some way. I guess maybe whether that's the surface structure itself or the composition, like you were talking about with before you mentioned the capacitive effect of like for Mott-Schottky would be impacted if your dopant isn't uniform, something like that, right?
Yeah, the charge is
effectively
different.
Anything of that nature, any heterogeneity, right, in your catalyst structure or composition, probably would lead to non-ideal capacitance, pseudocapacitance. I don't frankly know how to differentiate between those two things, to be perfectly honest. But it is not unreasonable to me to say that if your semicircle you're getting is not ideal for a capacitor when you do your circuit fit, that could mean there is pseudocapacitance. So I wouldn't rule it out, is what I'm telling you.
Okay. All right, so I have a question from Twitter. This is great. So Ayla, thank you for waiting. Hopefully, sorry, we sometimes it can take a while. And this is also good to know that Restream is finally taking questions.
Yeah, this is a new development.
Twitter.
It's like sucking in the questions from Twitter, so we can see, which is quite nice.
Yeah. So Ayla's asking, hi, how would one go about selecting noise filters for CV experiments using ultramicroelectrodes? Thank you. So this is a very good question. Let me get my screen back up. So there are a couple of things to consider or think about in my knowledge of looking for noise filters for ultramicroelectrodes. So first off, there's general electrical noise, just period. That's noise that's coming from room lights or things like that. So or instruments. If you have some kind of light bulb, that's going to cause some noise. So you're always so you could have noise from some other instrument that that's near your ultramicroelectrodes. I'm just gonna kind of there. That's your ultramicroelectrode. So one thing to think about or consider when doing cyclic voltammetry, and this really applies to any electrochemical system, is what type of stability filter, which is the kind of filter that you use when you're choosing parameters in a potentiostat. And so what ends up happening is from the kind of potentiostatic set point, which is here, and then this goes to your cell or another, this other electrometer type of thing. But there is counter electrodes back here. But the filter is this guy right here. There's a capacitor that's here. This is the thing that you're changing when you change your filter settings on your potentiostat. And so if you have you can think of it this way. If this capacitor is very small, it charges and responds very quickly. If this capacitor is very large, it charges and responds a bit more slowly. And in your electrochemical cell, so actually
I can hide the question.
Yeah. Thank you. So in your electrochemical cell, make sure I have the right font. Your working electrode, we can model it kind of as, charge transfer resistance. There's solution resistance, kind of IR, the RU sometimes is what it's called. And then there's electrical double layer capacitance. So this capacitor right here, and even this kind of RC circuit right here, has a time constant associated with it. There's this RC time constant associated with it. Because you have a microelectrode, your R and your C are usually going to be really, really small, which usually means that you're going to need a filter that can respond very quickly, because this is changing very fast, especially when you're doing a cyclic voltammetry experiment. You're going to want to select a filter that also moves very quickly. This is the case for ultramicroelectrodes, but at the same time, if you had a big macroscopic electrode, you may also need a bigger capacitor here to make sure that, it's responding on a fast enough time scale, because it takes way too long for this thing to respond, to charge, to get to the potential. You're going to start finding some oscillations. If your potentiostat thinks it's at a potential that it shouldn't be, you'll end up getting noise ultimately. So this is to say that ultimately, when you're determining the stability filter or a noise filter when using an ultramicroelectrode, you're going to want to pick probably the fastest fastest filter or the smallest capacitor that your potentiostat is capable of measuring. And so that's a thing just from an electrochemistry standpoint. There may be other software filters in your potentiostat that can take care of things like electrical noise and light noise and stuff like that. I drew a square that was supposed to be like an instrument, but it's just a square over here. Instrument. it's causing noise. So those are the things that's the thinking that I would employ when trying to choose the right filter setting when using an ultramicroelectrode, or really using any electrode for that matter. So hopefully that was helpful. Please let me know if you have questions.
There's a couple of them that, so there was a clarification, as it typically happens.
Yes.
We're answering, and then you type in your response as we're asking for a response, and then we see it later. So apologies. Sometimes there's a delay. As a general rule, thank you everybody who's asking questions, and apologies just broadly that electrochemistry is unfortunately not something that's like every question we can answer in 10 seconds. I wish we could, because we could get to everybody's like immediately. It just takes some time to talk about these complex topics. So definitely thank you for your patience. If you ask a question and you're waiting a few minutes for us to answer, we're
thank you.
doing as much as we can here. To finish up with Tafara, she had asked again about doing impedance on an electrolyte using platinum wire, what model should you use? And my general comment was, well, I don't know what your data looks like. And then you clarified the data is linear. So just to be clear, again, somewhat of the same answer. I can't exactly know the answer to this, but what I will say is if your data, when you say linear, is something like on a Nyquist plot, you just have this, like a straight line almost, or it's just like a straight line up, and this is z imaginary minus z imaginary, and this is z real. If there's something like this, you probably have two options. You have, this is a CPE. That's what Q means, in case you're not clear. Sometimes people put Z, sometimes you'll see, just for what it's worth, CPE like this. It's almost like a capacitor that's bent. So just to be clear, CPE. So it might be something like this, where you have some, R0 here, right? And because you're testing the electrolyte effectively on a platinum wire, there's no intercalation, de-intercalation, there's no charge transfer processes happening. You basically just have a capacitance on your platinum wire. And so you just have, and ideally, if it was a perfect capacitor, it would be a straight up and down line, 90 degrees, but there's probably some angle here. This is basically where your alpha, your CPE alpha might be anywhere between, 0.9 to 1, something like that, typically. The other possibility, it depends on the platinum you're using, if there's a porous material. There's a lot of unknowns for me, but the other option would be a transmission line. Sometimes that can happen if you're sort of doing these blocking boundary symmetrical cell kinds of tests to study the electrolyte transport properties, tortuosity, diffusivity. I've talked about some of these, and I did another webinar. It's on our YouTube channel if you want to check it out. Transmission lines are a rather complex topic. I'm not going to talk about it more, other than just to mention that sometimes this shape, where it kind of looks like a straight line, sometimes it's actually a little bit like there's a little bit of an inflection. If there's any change in the inflection in the data, sometimes a transmission line can be an effective and accurate way to represent that. And that's the most that I can probably say on that without seeing data. And then there was a follow-up to Assad, who was asking about the pseudo-capacitance in the electrochemical double layer. And so the follow-up here, and then I promise I'll stop talking for at least a couple minutes, it says, in my opinion, if the material has both the electrochemical double layer capacitance and Faradaic contribution, then we should get two semicircular arcs in the Nyquist plot. Am I right? Or both EDLC and Faradaic contributions can make a single arc. So yes, they can make a single arc. In fact, the most common manifestation that you see is a single arc for those kinds of things. It's actually the same thing that Alex just drew. I'm just going to draw it again. Basically, at your electrode surface, I'm drawing it sideways now for some reason.
The question.
Yeah. What's that?
I just hit the question for.
Oh, perfect. Thank you. Yeah, no problem. At your electrode surface, you might have your charge transfer resistance. That's your Faradaic process. And it's in parallel with the EDLC. Again, whether that's pseudo-capacitance, that whole, I'm not going to spend forever on that again, right? But the point is, let's just call this just DL for now, whether it's pseudo-capacitance or it's ED, I don't know, right? And then some kind of ohmic uncompensated resistance, or all that solution resistance. But this plot right here, this circuit, a leading resistor and resistor capacitor in parallel, it's called a Randall's element, on a Nyquist plot looks like that. It's just one semicircle. So it is possible for both Faradaic and non-Faradaic processes that are occurring to result in one semicircle. Multiple semicircles would actually, in theory, indicate possibly multiple Faradaic processes occurring, or at least multiple interfaces. Like you might have a substrate in a film that makes a semicircle sometimes, that is indicative of the interface, like multiple interfaces. If you have a layered catalyst, you can get things like that. But one semicircle does not mean one semicircle can mean you have both Faradaic and non-Faradaic, like capacitive effects taking place. So just to clarify that. Okay.
All right.
So there was actually a question. I don't want to talk forever.
No, it's all good.
Tarek had asked a question that he did mention. I did miss one of his
Oh, yeah,
questions.
yeah.
I can actually answer this quickly, and then please, I hope that you.
Yeah,
can
where
answer
was
one.
his? I didn't actually see his question.
I got it. Yeah,
I missed it.
I had missed it. It is true. This is why we did say at the beginning, please let us know if we missed your question. We're doing our best, and then sometimes we do miss it. So this was when fitting EIS data. What's the distinction between employing a weight factor of 1 versus the square of the absolute impedance magnitude? What's the recommendation? So effectively, the thing you're talking about here is the difference between unity and parametric weighting. Effectively, at least that's the way I see it, and the way, for example, in our software we describe it. So I'll show you that very briefly and give you my opinion. So in a circuit fit, when you're doing your fitting, it's how you weight the data. So parametric is, I don't know if it's exactly, to be honest, I don't 100% remember. I'll be perfectly honest. It's been a long time since I worked with our software team and coded all of this stuff into our software, and the exact formulas that we use, I don't actually 100% remember. It's not even like, I mean, if I did remember, I'm not sure I could perfectly share it with you because it's probably some, I don't know, proprietary thing, but also I don't remember, so I can't even share it with you. But the parametric weighting is something like what you said, which is to say that it's, whether it's the square of the impedance magnitude, or it's the imaginary impedance, or it's the phasing, something is weighted, right? The points are weighted. And then unity weighting is, as you said, every point is weighted by 1. So my recommendation is parametric. Generally speaking, gives the best result. That's why the default setting in our software, for example, uses parametric. That being said, a lot of the times, the answer to your question is trial and error. Sometimes weighting by 1 works better for some data sets, and sometimes the parametric, weighting works better. And sometimes for some data sets, both work okay, but one gets a better final fit. Like, and I've done in my webinars, for example, I think in one case I have like 2 data sets, and like one of them, the final fit works much better when you do unity, and the other one works terrible unless you do parametric. And it's like, that's one of the reasons why our software was designed the way it is, to allow you to switch actively between them and just go back and forth and see which one is better. Because I don't 100% know that I understand why. I just know that it happens. It's a weird mathematical algorithm kind of a thing. And for whatever reason, sometimes one works better. But generally speaking, for more situations, the parametric weighting is the most successful. That would be my recommendation. Okay, let's get back down and try to catch up now.
Yeah, we have a question from Naresh. I may need your help for this one. For cyclic voltammetry, I used 0 to 0.6 volt potential window, but for GCD, it's reaching 0.55 volts. And I have a different potential window for CV and GCD. So how would I defend this? Or I guess the question is really like, what's going on? Why are there seemingly 2 different, a 50 millivolt difference between the potential window in cyclic voltammetry and in GCD? I guess that I have a few questions, because GCD is supposed to be used for things like batteries. So do you have a 2 electrode cell versus a 3 electrode cell when doing CV versus GCD? That's perhaps one question. Are the electrochemical conditions different? So that's, I think, probably my first question. And then maybe my other question would have to do with the definition of your potential window. In galvanic static charge discharge, are you setting the current to such a level that, like, oh, if I reach this current in my CV, that's the point where I'm like, okay, I've reached this current because it started to curve up, and that is the potential window that I'm getting in CV. So that's kind of where I'm what I'm thinking about in terms of making sure that those numbers or values are the same. A 50 millivolt difference, it's not insignificant, but it's also It's also somewhat small, but I would think about those things. I
Yeah.
don't know.
I guess I agree with everything you said, and effectively, it's just an elaboration of everything you said. But
Mhm.
mainly, it's that I would question why you're claiming this. Like the limits of a CV and the limits of a galvanostatic charge discharge are subjective.
Mhm.
Like what? So like on a CV, right? If you I'm just gonna draw some random whatever, and it's like if you go really high, you'll start having oxygen evolution. Okay, whatever. And then you scan back, let's say you have some Faradaic process, and if you just scan negative enough, you'll have hydrogen evolution down there. Okay. So like what are my limits for my CV if I want to like study this process? It's here to here. I'm just making this up, right? But but I could also say it's here. I could say it's here. Okay, so this is 0.6 and this is 0.55 and this is those numbers everywhere. 6.5. I'm just saying there's some subjectivity. So when you say
yeah.
that, it's exactly what you said. I'm just trying to illustrate it,
Yeah.
right? And it's like, well, your limits for your CV, you just pick those, right? Like, I mean, are you using a particular metric? Like Alex was saying, like the current goes up, like by how much, right? And then similarly in your galvanostatic, let's say you're charging, right? And so you have this is capacity here or time basically, and this is voltage over here. And so this is 0.55 and this is 0.6. Okay. So as it's charging, maybe it hits here, it starts to shoot up. It's like done. It's done charging or discharging, whatever the case would be. Anode or cathode. Okay. Well, there's some subjectivity here. You're sort of saying, I'm sort of asking as well. Like, are you, it's done here because I think this has risen enough, but I think it should go to here. Like, it seems to me like you're sort of selecting those numbers, and maybe you have a good reason for doing so, but there's subjectivity in both of these experiments in terms of what the like upper limit is. And so I guess I wonder generally why you would propose a difference there, and again, I think probably the issue again, unfortunately, is that I would have to like see your data to know, and it might be that you just have to set those to be the same, like no matter what, to have that consistency, because
Mhm.
I don't know if I agree perhaps or even quite understand the idea that the way you stated it, which is to say that like it reached 0.55 volts. Like, does it, if you keep applying that current, does it not reach 0.6? Maybe it doesn't. Maybe there's a reason why it doesn't. That sounds like another kind of a problem, actually. If the voltage isn't getting high enough, something else is happening, perhaps. Right. But generally speaking, it seems to me like, you set the trigger potentials of your GCD wherever you want. And so I would say you should probably set them the same. That's just my feeling on this. So anyway, again, same sort of thing here. Feel free to clarify, if you have a follow-up. I know you said it was 3 electrode.
Yeah.
So that's good to know. But again, same sort of thing, is a bit of clarification would potentially help. And maybe that what I said will allow you to set them the same yourself. Like, you can choose, right? You can choose those limits of what makes sense based on the materials you're working with. King of Chemicals, I think, had some urgency. So let's try to get to
we
that.
can do this. It says either cyclic stability test is done only for device, or can we also run the stability test for a single electrode working in a 3 electrode system?
Yes, you can.
Oh,
Yeah.
so I'm assuming he has like maybe an electrochemical sensor or some kind of device, and he wants to just run it in the device, but could he also just do it in a 3 electrode cell and have the same results?
Do like 1,000 CVs and see how it survives or something.
Yeah.
Absolutely. Yeah,
Makes
absolutely.
sense.
In fact, that's one of the main ways that people test like oxygen reduction reaction catalysts, or related kinds of electrocatalysis. You don't have to make a full fuel cell, right? You do it a 3 electrode system, and you just cycle it 1 billion times until it dies, or
Yeah.
like,
and then
absolutely. That's a very legitimate and quite often used method for determining cyclic stability of a any kind of electrode, battery, fuel cell, whatever. For sure, you can do it as in a battery, it's called like a half cell, right, or something like that, or just a 3 electrode electric catalysis. That's certainly something that you can do.
Yes. Okay. So next we have Chin Tran. He's asking, how do capacitance determined through CV, cyclic voltammetry, compare or relate to those obtained from EIS, electrochemical impedance spectroscopy? They should be the same. They're just two techniques looking at the same phenomenon, ideally. EIS is a little bit more, I would say, specific because it's able to probe at different frequencies. So you can get a lot more information. But if you have one capacitor, if you're looking at electrical double layer capacitance, you can determine it through cyclic voltammetry, and you should get the same result as if you're doing it with EIS.
Yeah.
In an ideal world.
Yeah. I mean, the reality is you probably won't because measurements have some error to them and all that kind of stuff. And the other thing I guess I would add to that is the main difference, other than they're very different techniques. But one of the main differences between the EIS and CV tests that you would do in this regard is that the EIS is at one potential and the CV is moving. So if, for example, you did CV to try and get capacitance, but you had a really big potential window, maybe you would get a poorer estimation of the capacitance if you incorporated some Faradaic stuff by accident, right? It's possible.
Yeah, definitely.
Or similarly with impedance, if you pick a bad potential to do impedance and there's a lot of, impact of Faradaic process. Now in theory, it's just impedance is supposed to be able to account for that because by frequency. But I'm just, the potentials that you pick might matter and might impact that. So, the most ideal situation is that you don't have anything Faradaic happening. If you're just trying to study like supercapacitance or like EDLC or whatever it is, right? You would have like a neutral potential for your impedance set point, whether it's OCP or whatever, and then a similar range of potentials for your CV, and not that big of not like plus or minus a volt, right? Like maybe like a couple hundred millivolts at most or something. And then, as Alex said, in theory, they should be the same.
Let's see. So Tarek has, I think, some follow-up. I think this is related to the question I answered with Aleo, which is about the noise filter and stuff like that. And he says, talk about bandwidth parameter of a potentiostat. So, I mean, I can confirm these things with our electrical engineer. And he's right in this case. I am adjusting the speed at with which the feedback loop is altered by changing the stability filter, because it is just like, well, how quickly am I adjusting the response to the electrochemical response? My understanding of bandwidth is mostly like an operational amplifier's bandwidth just means what frequency of potentials it can take. So if something has a large bandwidth, it can take a wide range of frequencies it can accept and also output as well. But I can double check, as my understanding of bandwidth is limited. But and then on that note, do Pine potentiostats provide an automatic bandwidth feature, eliminating the need to manually choose? I don't know what the numbers 1 through 9 refer to when it comes to bandwidth.
Someone else's potentiostat. Sometimes I've seen with things like this. This is my guess about what he means is, I think sometimes with other some of our other companies that make potentiostats, it's like, it's almost like, I don't know a better way to say it, dumb it down almost, but like simplify it for the user, where it's like, you'll have like instead of the short answer is that yes, we have like very comprehensive filter settings in our potentiostats and our software. You can choose the frequency value of the low pass filter. You can pick the capacitance value of the capacitor that, as you said, is slowing down the feedback loop. We have all of those options pretty comprehensively in our software. I think that some of our competitors handle that in a very simplified manner by having like a speed setting.
Yeah.
And it's like 1 through 8, 1 through 9.
Yeah.
And it's like, what does that even mean? It's like, I don't know.
Yeah.
3.
Yeah.
It's slower, like, or So
Yeah.
you don't really know what it's doing. We like to have it where we have like the frequency associated or the
Yeah.
capacitance associated
Yeah.
with that filter, because you might be a pretty, like intuitive researcher where you say like, well, I definitely need to, it's like a low pass filter. So it's like, well, I have noise at, 60 hertz. So I want to
Mhm.
have a response filter at 15 hertz that really cuts out any of that 60, 50 hertz noise.
Yeah.
Like, like things like that. So it's like, if I just have speed setting 2, what is that? Is that low enough or high enough, So we try to be, we do actually have pretty comprehensive kind of stuff like that.
Yeah.
We try to be pretty, it's a trade-off, right? Because it's like, as a company, if we provide like super filtered data, it'll
Mhm.
look really clean probably in most situations.
Yeah.
The downside is it might cut out the noise that is actually your experiment, right?
Yeah,
Like
your real signal.
yeah, it might get rid of the signal you're trying to look at, right?
Yeah.
And it's also not honest to like filter the data beyond recognition, to have it be like so
Mhm.
perfectly smooth. Like electrochemical data is ugly reality,
Oh yeah.
right? Like the raw
Absolutely.
signals are so gross. Now you have to filter it a little bit. Like,
Yeah, that's right.
so I'm not saying we don't like filter and clean the data up. Obviously we do, to in my opinion, a pretty reasonable degree,
Yeah.
let's just say. But a lot of these tools that you're asking about that we do provide, for example, in like the filtering tabs of, experiments, allow you to more like, intelligently and tune all those different knobs if you
Mhm.
want to
Yeah.
really hone your signal down. And it's actually really critical for some experiments, like
Oh yeah, absolutely.
LPR measurements for corrosion need like really tuned up. Anyway, whatever. The response filters need to be really kind of honed in to have it be smooth for a really slow experiment. And like fast experiments, you can't filter too much, or you'll like EIS, you'll filter the signal out. So there's
Oh,
a lot
yeah,
of
yeah,
like
that's right.
considerations, right? Where having those knobs can really help you if you want to have that troubleshooting acumen, right? To hone in
Yeah.
on the best signal, basically. So
Yeah. Yeah. I think we got through.
I think we got everything.
Okay, yeah, we got through everything. Great. It was fantastic.
Well, King of Chemicals was saying that his phone battery was dying, so you're going to want to charge it.
Yeah.
So you're going to want to apply a positive current, and that will charge your phone,
Yeah.
and then you can continue using it. So that's my advice to you.
I have wondered. I think one of our colleagues actually forgot his charger and used the potentiostat to
Yeah.
charge a device. I was like, I mean, I guess it says you can put +3 milliamps, but how do you know which terminal it's going in?
It feels like a dangerous thing to me as well, because
Do OCP first.
well, yeah, I
And
think it's
then-
dangerous because anyway, the battery management system in a phone or other like consumer electronics device is not exactly as simple as like just pump a bunch of current into it and it's good.
Oh yeah,
It's like
yeah,
there's like, the potentiostat is going to do it
yeah. Whatever.
forever.
Tell it.
And you don't know what the voltage is supposed to be. When you plug in your charger, there's like microchips that know, that are talking whatever, they know what voltage it should be. And that's why you can plug in your phone for 12 hours. It's done charging after, 3 hours or whatever. And it doesn't blow up your phone by continuing to charge it. Like it
Yes.
stops.
Yeah. There's some intelligence to it.
So yeah, using a potentiostat is a really like clever and very nerdy, fun way to charge your phone if you forget your charger. But I would be scared to do that. I'd be afraid I'd destroy my phone by accident.
Yeah. And I would too. All right. We have another comment from Chintron. I agree that the capacitances should theoretically be the same, but capacitance evaluated through CV affected by the scan rates, while evaluated through EIS affected by the frequency and potential. And then his follow-up is, how do we represent those capacitances in relation? So one thing that's interesting I want to kind of point out is it's Neil's favorite equation that he doesn't sometimes remember.
The Butler-Volmer equation?
No, the current for a capacitor.
Oh, I can't ever remember it. Wait, I is equal to C times the scan rate.
Yeah, that's right.
Yes!
C dV dt.
I'm getting it.
You are getting it.
It's like 41 episodes of weeks of doing a year. It's taken me a year to remember a simple, but I got it. Anyway, please continue.
Oh yeah, so the current associated with the capacitance, and this comes from taking the derivative, the time derivative of just the charge is equal to the capacitance times the voltage, right? So just the time derivative gives you this, and so when you do a CV, your capacitance always looks a little something like this, like a square, something like that. But as you increase, when you do a scan rate study and you're adjusting this dV/dt, your current is going to increase, right?
Yeah.
So as you adjust the scan rate, you're going to get a proportionally larger and larger current associated with double layer charging, all kind of centered around 0. If you had like a perfect capacitor. And so this is one thing I always like to, tell people that's useful in electrochemistry. One of the reasons the double layer is so annoying is that you think like, oh, well, I got the Randall-Sevcich equation. I can increase my scan rate to get more current. Well, yeah, but there's a square root of scan rate dependence on the current for your Faradaic process, but there's a linear relationship with double layer charging. So your double layer charging is always going to beat it in terms of if you just keep going faster
than your peak does.
Yeah,
basically.
So that is how. So I just want to make sure like this value stays constant when you're doing something like this, and you're just kind of going to faster and faster scan rates. So I just wanted to make that clear. Now I don't know, and maybe Neil can comment more about this, about the frequency change, or maybe the potential change, with Chin's question, which is while evaluated through EIS affected by the frequency and the potential. So yeah,
you can think about it in a very similar way.
Yeah.
Right. What Alex just drew, to kind of make it a little bit simpler, right, is that as you scan faster, the current is bigger, right? Impedance by frequency is kind of like changing the scan rate. It's a similar phenomenon, right? So as you are having faster frequencies, right, you'll have a different current than at lower frequencies. And it's because the resistance is changing. I'm not sure if it's perfectly analogous. I have to think about it a little bit more. But anyway, just generally speaking, it's like by frequency, the capacitance is the same. It's you're probing the capacitance, but the current, just like what Alex drew, right? The current is changing as dV/dt, or the scan rate changes. So similarly, the current response is changing. Basically you can think like by Ohm's law as the frequency changes, right?
Yeah. And you know that the impedance of a capacitor is inversely related to the frequency. So you can you think about it the opposite way, which is that you actually get quite a bit of current at high frequencies for capacitance. That's the same as having a very, very fast scan rate. That's like that's another analogous way of thinking about EIS and CV from like a speed time relationship.
Right. And then the other general comment about that is that you seem to be sort of laboring under this idea that because EIS and CV are obtaining the capacitance through different methods, that they're not comparable. And I don't know why you would necessarily think that, to be perfectly honest. Like, yeah, they're different, like fundamental, right? One's AC, one's DC, they're different techniques, and they're coming to the solution through different ways. One through scan rate, right, and one through frequency. So, right, like that should be my response. Like, okay, yeah. Right.
They're going to be the same.
They're both like valid ways electrochemically to probe something fundamental about your system, which is the capacitance. So it's great. In fact, the tricky thing is that, again, practically, probably, and unfortunately, you might end up with slightly different values when you do this, and that's just unfortunately the nature of the beast, right? So you might have to have some trial and error, or pick one, for example, to use as a compare. Like maybe you're testing multiple different materials,
Mhm.
you know, and you want to compare. Well, you wouldn't want to compare the CV of one with the EIS of another.
Yeah.
You know, so you might pick one technique to use as your metric. And, you know, there's, again, it's like there's positives and negatives to everything. You know, you might pick CV, for example, because it's easier or something, right? Or maybe you don't even have an EIS potentiostat, or maybe you pick EIS because it's quicker and less invasive, you know, but then
Yeah.
you have to deal with the circuit fitting, and maybe the circuit fitting isn't always easy, right? Maybe it's
Yeah,
like, maybe
that's
there's
also
some
true.
noise. And so that makes it inaccurate, you know? So you might have to kind of do some of your own, I don't know, trial and error, or selecting which one you think would be the best if they're not like really close. You know what I mean?
Mhm.
Like, what if one is one like an order of magnitude higher, and you're like, oh shoot,
Oh,
which
yeah.
one's accurate? And so, you know,
Yeah.
you might be in trouble, right? So you just have to pick the one you feel is most, maybe compare it with literature or something like that, right? But yeah, I hope that does kind of help clear that up for you.
Yeah. I would imagine like you should get slightly different values
Yeah.
of capacitance just because of the nature of like, but yeah, if it's an order of magnitude off, like no, I don't. Then there's something off.
Yeah,
It is
something is
actually very
strange.
interesting because electrochemistry, a lot of the techniques, you actually can. The phrase actually I heard a professor say is it's like many ways to skin a cat. You can calculate the diffusion coefficient so many different ways in electrochemistry. There's so many techniques
Yeah.
that allow you to get that information. So similarly, there's several ways to get the capacitance for some electrochemical systems. All right, so it looks like just gonna check to see if there are any
I
other
think we're good. I think
questions
if
from
you want
other
to,
people.
because this is always the time, there's a lull, and then in about probably 6-7 minutes, we're going to get
Yeah.
a deluge of questions.
Yeah.
If you want to talk about the IR compensation thing, now's
Yeah,
probably a
sure.
good time.
So there was a question on the last live stream where a guy well, I talked to him afterwards, which you can too if you want to reach out to us via email, and then we can have a further conversation. But wait, it looks like did Tarek just ask I think Tarek asked another quick question. I do want to try to answer questions from people right live. So I'll get to the other thing later then. What's the optimal method for sampling the current response at specific time intervals? I've heard that this is one of the trickiest aspects of constructing a potentiostat. So the optimal method for sampling the current response. Well, ideally, you want to have smooth data. You don't want to oversample because then you're going to have lots and lots and lots of data points that could look kind of noisy. And you don't want to undersample because you might be missing something and your data won't look smooth. It'll look kind of jagged. You'll have these jagged data points here and there. So it all depends on your electrochemical system, right? Like from what I answered Ayla's Elia's question, depending on the kind of the RC time constant of your working electrode, the time and even also on that case, the scan rate of the CV, the frequency or the choice of stability filter or choice of capacitor in feedback with that amplifier is going to make an impact on how quickly you're able to sample. So that's another type of thing. But that again, that sometimes it's a little bit of trial and error. But yeah, you're trying to sample like the potentiostat can sample current really, really fast, but the data points that you pick from that sampling is also another thing. So hopefully that's that kind of helps you, Tarek.
There's also the whole, sort of fundamental thing about some experiments require more data, some require fewer data points
Yeah.
from the perspective of filling up your computer's hard drive too fast.
Yeah.
And some require a non-uniform, non-linear, asymmetric kind of rate of data acquisition, which is tricky. Like battery experiments, for example, often require a lot of data and then not a lot of data and then a lot of data. So you want to take you'll have things where you like record a data point every 10 seconds, or when the voltage or the current changes by a certain amount. So that can be hard as well. And the other part of your question, trickier aspects of constructing a potentiostat. So in some respect, it's if what you're sort of asking is a more electrical engineering question about the design and fabrication and construction of a potentiostat, that is a bit above my level of understanding perfectly well. Although all I can say to that is that, that gets into some of the other things, which are like to a certain degree, even if tell your software only give me a point every 25 minutes, it's still collecting data a lot. It's just not showing you because that's what you asked for. Yeah. So there's two different things here. One is that what you see on the screen as far as the data frequency and the sampling time and the current response in the intervals. And the other is that the sampling interval and the collection, characteristics of the instrument itself. And those are different things, right?
Yeah.
And again, all I can say to my level of understanding and knowledge is that potentiostats are often collecting a lot of data and then decimating it. And that's a kind of a continuous process that occurs. What they send to the computer, right, or the the software to display for you, is not always the same as the amount of data they're collecting. There's stuff that goes into that, an ADC converter and those kinds of things, and also the bit rate. There's a lot right there. So it's definitely a ball of wax, I guess I would say.
Yeah. I think another thing I would also mention is there's the speed of acquiring data, but there's also the speed of the electrochemical system, and there's the speed of the electronics itself. And so you kind of know this a little bit from EIS, that like, you can get stray cable capacitance at very high frequencies, or inductance, cable inductance at high frequencies. And it's like, that's like all the electronics inside of the potentiostat can also contribute to the signal itself that you're measuring. So you're right, and some of those things will only manifest themselves at super fast speeds, and that also affects things like the current interrupt method, for example. Like in current interrupt, you're disconnecting the counter electrode for a brief period of time and trying to sample as fast as you can to get the solution resistance. But you can also have inaccuracies because you sample so fast that you're actually collecting data from other parts of the potentiostat that'll erroneously get put into your system. So this is all like crazy stuff you'd only learn if you were
other parts of the potentiostat.
Oh yeah, absolutely.
Yeah.
Let's see. There's another question. I think, Chin made a comment, which was just, it's true. I got a little bit confused regarding the differences of DC and AC techniques and also the fitting accuracy. Also, there's a misunderstanding of capacitance and specific capacitances, but he thanks us for the clarification.
Clear for you now, but again, just let us know if you need to discuss anything more about that.
Yeah. And then we have Teresa. I'm a graduate student and want to know your opinion about microelectrodes. I read all the positive aspects that they are reported in the literature, but my voltammograms were full of noise and useless.
Welcome to the club.
Yeah.
Yeah.
Microelectrodes, there's actually a lot of like equations that make the current response of microelectrodes like very nice compared to other electrochemical techniques, but they are super prone to noise because you're measuring nano or picoamp noise levels.
Yeah.
So you have to have a lot of like filtering. You need to have Faraday cages. You need to, even dark rooms or stuff like that.
Potentiostat needs to float usually to, eliminate as many external sources of noise as you can. Because the currents are so small, you're just going to be prone to noise. You got to make sure you're using a very sensitive potentiostat with a very sensitive current range. Like if you're using a 1 amp range, the resolution of your current is going to be, microamps, and you're measuring nano and picoamps, so there's things like that are considerations, and probably partly why there's noise in your voltammograms, but also, the fabrication itself of microelectrodes. Again, I don't know if you're making them yourself or you're purchasing them. There may be some companies that we don't make we don't make microelectrodes. We make, macroelectrodes. Yeah, well, I guess technically they are, right?
The traditional electrodes.
Yeah, exactly. Like millimeters sized, right?
Yeah.
Stuff. I haven't tried myself, but like, for example, I know like the electrochemistry folks often make like fiber electrodes. And I don't know if that's exactly, it's a little different application, right? It's for like brain chemistry studies, but like microelectrodes often use these like thin fibers. Sometimes there's a shroud in glass or something like that. Yeah. And it's just, I know, like, not from experience, but just from, working here and experiences with other people telling me, it's like you'll make like 10 of them and 2 are work, 2, like 8 of them fail, and 2 work. So even from the perspective of like, if your voltammograms are noisy, it might be from all the stuff that, you mentioned before about the potentiostat and the filtering and the noise at Faraday cages. Yeah. And maybe just making the electrode itself was fraught, like it didn't work well. So, I think that all the positive aspects in the literature and all of the positive studies that you see about them are certainly like valid. They're just the minority of tests and electrodes that were used. It's like it just has a low success rate. It's just hard. It's hard, right? It's just hard. That doesn't mean that it's not positive and it's not worthwhile and you shouldn't keep at it, right? But it is tremendously like electrochemistry itself is hard. Yeah. Right. And then you make your electrodes micro, Oh yeah. You're like upping the difficulty level on an already difficult, field of study. So, I would not be so discouraged. It's just going to take more practice probably. And, experimental considerations, unfortunately, than other folks have studying, macro regular, so to speak. When you're getting microamps and milliamps, like you don't care about picoamp noise, right? But when you're studying picoamp noise is a problem. You're kind of up against it here. So I guess I just try to be encouraging and say, keep at it, keep practicing, keep trying. You might just it might take some time to get there, is my guess, because there's all those kinds of considerations to fight against. And I think also the size of the microelectrode plays a role too. But it's like, size. If it's like, is it like 100 microns, or is it like 50 microns, or is it even like 10 microns? It's like all those things also can play a role in the data that you're getting. So, but it's definitely it can be challenging. But I don't know what exactly you're studying, but I might start with just doing like using a commercial microelectrode, with a known radius or diameter or something well constructed, and then study ruthenium hexamine or ferrocyanide, like a well characterized electrochemical system, and you should get these S-shaped voltammograms. And that at least helps you know that, like, hey, I can do this experiment. Like I can use a microelectrode. It's then like, yes, when you're trying to do research of something, it's like, okay, that's where things become more difficult. But demonstrate to yourself that you can use these, and it's not just your skill. It's like, oh, you can do this. The chemistry that you're studying is just very hard, but you can use these. Yeah, for sure.
All right, so that was a nice, quick burst of some questions.
Before somebody asks a question,
yes.
I'm just kidding. If you have a question, please feel free to answer it. Go into the IR comp thing.
Sure.
We're trying to prioritize the live questions, obviously, but
as they come.
I think this is an interesting topic, so I want you to talk about it.
Oh, okay, yeah. So Adam was talking to me earlier this week about an interesting thing per se, but the idea, he sent me a paper, and I will share this paper. Let me see if I can find. Does it not? Yeah, here we go. So this was a paper that was published 2 years ago, so 2022. Why careful IR compensation reporting of electrode potentials are critical for CO2 reduction. And this guy was having some issues with just doing IR compensation, making sure he had the correct value and stuff like that, the correct value for the resistance. So so this is a short letter, because it is a letter, so it's only a few pages. But one of the interesting things that they're mentioning is that the Faradaic efficiency for the CO2 reduction reactions that people are calculating is heavily dependent on the actual potential that's being applied. And when you use IR compensation, you're adding some additional potential to take into account changes in the resistance or whatever the resistance is. Now, the most interesting thing that I think came about this whole paper is here, figure 4, which is that as you do a bulk electrolysis experiment over the course of hours, the solution resistance will actually start to change. And this is kind of crazy. It's just like, for a traditional 3 electrode CV experiment where you're just, doing a small analytical experiment, no problem. Solution resistance is constant. But if you're doing bulk electrolysis and stuff is changing, then as your solution resistance is going down or changing dynamically during the experiment, it means that the static resistance value that you calculated prior to doing your bulk electrolysis might actually not be correct, or it would be changing the actual potential that you're applying. And in this paper, they make a point that a 100 millivolt difference or even a 35 or 30 millivolt difference could make a huge difference in the Faradaic efficiency that's actually reported. And so what I'd like to at least share with you, or at least the thought process is, how on earth how can we measure the dynamic change in the during a bulk electrolysis experiment? So I don't think there's really a great answer to this, because while you're doing bulk electrolysis, this is time, and you're measuring current, and you are applying, you're applying some E to this system. So there's an E applied. Okay. Applied. There's an E there. So you would typically get something like this. It's almost like a chronoamperagram, and then like the current just kind of goes like this. Maybe it changes a little bit throughout the experiment, but at different times, and this could be like hours, right? Hours of timers going by. And you have IR compensation on. So you have I, and then you have R, and you set this to maybe some value. Maybe you have 200 ohms of resistance. At this point, like that's the starting point. You have 200 ohms. But then as time goes on, maybe it changes. Maybe it's like 180 ohms. And then maybe here it's different. Maybe it's something like, 160, etc. ohms. So how do you account for this? Because now your solution resistance has changed because the makeup of the bulk electrolyte is different. So what we have proposed, or one way to do this or solve for this, because I think this is a big problem, especially with so many people who are doing CO2 reduction, is because this is hours of time, you can effectively stop the experiment at different times and perform a very quick experiment to determine the IR compensation. So maybe this is something like EIS, or something like a current interrupt, or something like positive feedback. So you may be able to have these intervals where you're like, okay, I'm going to stop what I'm doing. I'm going to stop applying, say, -1 volt my system, and I'm going to do EIS. Well, maybe you do EIS at like a baseline of -1, and then you have a sine wave about -1, and then you calculate the resistance value. And what I've learned is that our potentiostat, there are ways to program it so that, okay, I do a bulk electrolysis experiment, I stop it, I switch to doing EIS, I get a new calculated resistance value, and then in the next bulk electrolysis experiment, I can apply that same resistance value with, say, 80% or 90% compensation. And the idea is you want these techniques to be performed as fast as possible, because very fast. You want this to be as fast as possible because you don't want to interrupt your system for very long periods of time. Because during this EIS experiment, if it's about -1 volt, there's effectively some charge that you're missing in the experiment, right? So you want to have this maybe to be like, a few seconds if you can. Just do some very high frequency EIS experiments and then get the resistance value, plug it in, and then see how it changes, continue the experiment. And depending on what your system is, you may want to do this, every 1 hour, every 2 hours. If I look back at the paper, it looks like it's going down by a few ohms of resistance in this particular system. It went down by, let's say, about 6 ohms after an hour. So maybe if you're doing a 5-hour long experiment, you change it, every hour you adjust it so that you account for those 6 ohms of resistance. So when you're calculating the Faradaic efficiency, you need to keep in mind the points with which you stopped and measured the resistance and then continued on to calculate, as well as the adjustments in the resistance over time. So this is almost to say that I think there are ways to kind of mid-experiment dynamically measure the solution resistance and account for it, but it does mean that calculations of the Faradaic efficiency are much more complicated as a result. But I think that's also just the advancement of science, is that you have more accurate, better techniques, especially when you're looking at CO2 reduction in particular. So
yeah, the only thing I was going to add to this is that it just kind of, there's a sort of analogous type experiment that people in the battery world sometimes do, which is that they want to get instantaneous and as simultaneous as possible, or as instantaneous as possible, measurements of the state of health or the state of charge of your battery. And so one of the ways that people have tried to do this is impedance. The impedance experiment often requires you to, like, if you're charging up a battery, people do experiments where they charge it up for a bit, they stop charging, they wait for it to be steady, they do impedance, and they keep charging. It's similar to what Alex was talking about. It's like you're applying your chronoamperometry or whatever. You stop for a bit to get the IR, or in the battery case, it's like getting you're getting resistance maybe with impedance, but you're getting some measure of the battery, how it's doing. That's impedance kind of generally gives you that information. So one of the ideas, and I actually studied some of this when I was a postdoc, but it's like, can I just do it without stopping? And the answer is kind of yes, but kind of no. It depends. And it's similar to what you were doing. It's like, you could kind of keep applying and remeasure, and then you got to adjust. And it's like, it's tricky. Like how much was the current, how much time was lost, current loss, do you have to adjust for that? It's tricky. So it's a similar thing. It's like, if you want to do impedance on a battery, or even a CO2 reduction thing, in the middle of it, and I'm speaking specifically for impedance now, less about current interrupter, things like that. If the potential and the current is relatively stable at that point in time, and you do impedance on it, great, because it needs to be stable, for it to be valid. But it's like, if it's, and that means either that you're not in a place where the current is decaying like crazy or moving or whatever, because if it is, it's like, your impedance data is probably not that accurate. Or if the impedance test takes too long, the good thing about IR compensation is it takes a short amount of high frequency, so it's over quickly.
Yeah.
You can kind of zap it real quick. Just
You can optimize it too.
Yeah.
You don't have to do a full experiment.
Exactly. In batteries, it is not always so lucky. In fact, a lot of times the high frequencies are irrelevant. You just probe inductance. So you have to do a bit of a range of lower frequencies. And if it takes too long or perturbs the system too much, it's like you're going to be in trouble. Anyway, all of that is to say that this is a cool idea. I like this because it's like, it kind of speaks to the idea of like, it's doing two things at once with your electrochemistry. It's like doing the electrochemistry itself, the reduction, the charge to discharge, the whatever, right?
Yeah.
And probing something related to that at the same time.
Correct.
It's really cool. I mean, it's like next level electrochemistry.
Next level electrochemistry.
Yeah.
That's right.
Does that show is like Next Level Chef? I haven't
Next
seen
Level
it.
Chef.
Yeah.
Oh.
It's like, I think it's like a Gordon Ramsay show. I like Gordon Ramsay. He's a chef. Do you know Gordon Ramsay?
Yeah.
Okay.
I just know he like shouts at people.
Yeah, he yells at everybody and swears a lot and spits food out, and then at the end of the day likes the food because he fixes the restaurant, and so you have to like the food at the end. I like those shows. I like a lot of those cooking shows where like they fix the restaurants and stuff. That's that's one of my favorite kind of style of show. Anyway, I have no idea. I haven't seen the show. I don't know what it is. I just have seen a preview for it once or twice, and it looks like it's like they're cooking on levels of platforms above each other.
Okay.
And I don't know why.
Oh.
But that's what we're doing here.
Oh, yes.
You're doing CO2 reduction, and it's underneath IR compensation, or the other way around.
The other way around.
It's next
Nested
level echem.
into it. Yeah.
Next level echem.
Next level echem.
I bet if Gordon Ramsay hosts Next Level Echem, I would watch it. It's like I just picture this like a grad student in the lab, and Gordon Ramsay's he's like clicking buttons. He's like getting his counter electrode in his cell, and Gordon Ramsay's behind him, and then just starts yelling at him. He's like, "Ah!" And he breaks his cell. It's just like berating a grad student or something.
Berating a grad student. Grad students already have to deal with berating. Speaking of berating, it looks like the next question that we have.
This is a good one. Yeah, Fernando says, "How do you survive peer review hell?" Yeah. So I assume that you're, graduate student or a postdoc or something, and you're working on getting some publications out. And perhaps because of this question, you might be trying to break the ice, so to speak, and get the first couple of publications out the door, right? Because it takes some getting used to this process. So I'll just give you a few bits of advice, I guess, that I learned when I started grad school and trying to get publications out and everything. The first is that you want, so the process is you write a manuscript, you submit it to journal, and they come back and they never say, "Great paper, let's publish it." That never happens.
Yeah.
Right. It's always, "Oh, we like it, but the 3 reviewers that we sent it out to have all these comments, and you have to do all these changes, and then they're never happy and whatever." So the first thing is that you literally have to kiss the butt of everybody who reviewed your paper. Like, you have to write a rebuttal letter. So you make a Word document or something, and you start by saying, "Thank you to the reviewers for their time and attention." And then you say, "Okay, reviewer 1 wrote, their point 1 was, this is the worst paper I've ever read. Everything in it is terrible. All the data is bad. You should, whatever their comments are, right? Whether, it's probably not like that, but it's probably like, this or that." You always want to like be very deferential and be like, this is an excellent point by the reviewer. Like, some of the answers to the reviewer questions, you're going to say no. Like, you'll get reviewers who are like, "Oh, this is interesting, but have you thought of this?" And they just like propose that you add like a whole nother paper to your paper worth of work. And it's just like, yeah, that's easy for you to say. I'm not going back into the lab for like 3 more years just to get this paper out. Like, this is either good or it's not, but I think it's enough data to publish. And you get reviewers that get, sticky kinds of, comments about wanting like way more stuff. Now, sometimes it's like, "Oh, just add this data set. I want to know," and it's like, "Okay, fine. I can go, maybe you do have to go get a little more data to appease the reviewers or because it's a good point, but some of the points the reviewers are going to make, frankly, are either going to be outrageous, or you're just going to be like, "I don't think that's necessary. I don't want to." So you have to be very deferential and complimentary. You have to be like, this is an excellent point by the reviewer. They bring up they bring up a very smart whatever, and you have to kind of like that's the way to handle this, right? And you have to be like, in our particular situation, we are likely to address this in a future, or we have addressed this in these other publications previously. In this paper, we focused mainly on XYZ, not Q that you've suggested. But what we've done is added a few lines on page 17 to discuss the, interest of this kind of, like, you add a sentence somewhere, right? Highlighted in red to say this is what we added. That's like, it may be of interest to the scientific community for this other thing that they've suggested to be studied, or we are doing that in a future collaboration. So like you say something like that, but like, this is practically how you get yourself out of when a reviewer basically wants you to add 9 years of your life to get one paper out of work, because that happens sometimes and it's a pain, right?
Yeah.
So you have to be like really complimentary. You add a couple of sentences to acknowledge what they said, and then you politely say like, this is not appropriate for this manuscript, but we appreciate it and we've acknowledged that. Like, that's kind of how you handle that situation, right? And you'll end up doing that a lot with your responses to reviewers. It's like you have to be very, very polite and overly like, excellent comment, great comment. And some of them will be. I'm being overly cynical here, and perhaps that's a little bit much. Because frankly, sometimes the peer reviews, to be fair, that's what it's for. They'll read your paper with a critical eye and find things that perhaps are lacking or needing or something. So to be fair, there might be comments that are worthwhile. Okay. And in those situations, you don't have to even lie. You can say, great comments, I have added that, paragraph to my paper. Okay, fine. But I think that's really the key. It's that, a lot of times, I'll just be honest here, you're dealing with reviewers who are, in the academia world. And there's a lot of egos to stroke. And, it's like a reviewer that takes the time to read your paper, from the editor of the journal, who, they have an opinion, whether it's all right or all wrong or somewhere in the middle, they're not going to be appreciative when they get the response back from the editor that says, they just don't like any of the comments you made. Because I've reviewed papers too, like since I've finished graduate school, I've reviewed a lot of papers. And I've never given anyone a bad review. No, I'm just kidding. But it happens. Like, you give your honest opinion and you give things you think are good or bad or whatever. And then the editor comes back and you get the response the authors have to the reviews. And sometimes if they're like, totally dismissive of any of the points you made, it bugs you as a reviewer. And then as a reviewer, you get to make a recommendation to the editor. And, hopefully the recommendation is something like, it almost always, like I said, it's almost never like just publish. It's always like published with some small revisions or whatever it is. But if you, as a reviewer, you're not satisfied with the author, you think they just ignored your comments and said, nah, I don't really want to do any of that. But my recommendation is don't publish, and the editor can ultimately do kind of what they want, I think. But that's the point of the peer review. It's like if sometimes just one, but especially all of the reviewers don't recommend publication, it's not going to get published, So it really does pay to be very polite, deferential, and diplomatic in how you respond to the reviewers. You kind of have to stroke that ego a little bit and, oh, that's a great comment, and add a sentence that, mentions, oh, this is a consideration, this could be why something's happening. Even if you're not 100%, it wasn't a point you were initially trying to make, try to really do that as much as you can. And then really the only other advice I have is that, frankly, this is one of these things. It's just the reality. It is what it is. I'm just being honest about this world of publishing, is that a lot of folks have this sort of thing. It's like there's some paper, some journals, Angewandte and Nature and Science and PNAS and JAX, that are really high impact factor. And then there are some other journals that are perfectly fine, but lower impact factor. There's obviously a range of journal impact factor and whatever accessibility and how how they're regarded, let's just say.
Yeah.
And so some folks make a paper and they just submit it to Nature, and Nature says no. And then they submit it to, they just go down the line of impact factors of journals, and it's like eventually one accepts it. That happens, and I'm not saying it's right or wrong necessarily. In some sense, it's like, it feels like it's like scamming a little, it's like if the paper is rejectable, then it shouldn't be published. But on the other hand, it's actually not unreasonable, because you might have a perfectly interesting paper, but it's not like the most impactful thing in the world. And so perhaps it doesn't belong in the Journal of Science or Nature or something, but it's perfectly legitimate research for the scientific community. And so publish it somewhere else, So if you get rejections, it doesn't mean you can't submit it somewhere else. It might just be that wasn't the right journal for your publication. You can try to submit it somewhere else. And sometimes you submit it and they'll ask if it's been submitted somewhere else. You can just say yes. You don't have to, be dishonest about that. It doesn't automatically mean that it will be rejected from the new journal. There's no, if it's been published by one journal, you can't submit it to another. That's illegal. But my point is that there's nothing wrong or immoral or unethical about, you got a paper rejected from one particular journal, you can submit it to a different journal. That's perfectly legitimate. So I hope that's if nothing else, some advice or some commiseration about it. And I do wish you luck. I hope you're able to get yourself some publications and, keep your career going.
Yeah, absolutely. So best of luck, Fernando.
Yeah.
Well, I think that's it.
I
think that's it. So hope that you enjoyed this episode of Ask Us Anything about electrochemistry. And stay tuned for more stuff on Pine Research. Check out the Electrochemistry podcast. New episode came out yesterday, and we will see you next week.
All right. Have a good weekend, everybody. Have a good week.
Bye.
Take it easy.